Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are discussing the paper data structures, in which we are going to talk about balanced binary search trees and AVL trees. We have discussed binary search trees in the last two modules. Here we are going to talk about balanced binary search trees. So, these are the people responsible for the development of this module. So, let us look at the learning objectives of this module. In fact, this AVL trees, the important balanced binary search trees, we are covering in two modules. So, the first module will give you an introduction, okay, and some operations. So, first before we go to AVL search trees, we are going to understand the concept of balanced binary search trees. We are going to look at the concept of balanced binary search trees. What do we mean by that? Why do we need it, and so on, and then we discuss the properties of AVL trees. This is one type of balanced binary search tree. So, we discuss some of the properties of AVL trees. Then we describe what is called a single rotation of AVL trees, and then we describe double rotation of AVL trees. Now, these rotations are needed in order to obtain balance. We will go into details about this as we go along. So, the keywords here are balancing, AVL trees, single and double rotation. So, let us look at balanced binary search trees. Now, as a tree becomes more and more unbalanced, the search running time increases from order of log n to the order of n. Now, before we go to this, let me just explain to you that these binary search trees are a very important data structures in many search operations. For example, in a database, in any place where you want to search, they organize it as a binary search tree. Now, as a tree becomes more and more unbalanced, I have not told you what is balanced, but what it means is as the tree becomes one side it keeps growing, the other side it is not growing, then what happens, the spread of the nodes in the tree is not uniform, and therefore, the search running time, the running time for a search operation of that binary search tree increases from order of log n to the order of n. So, average if you have it in the same the node spread uniformly, I will tell you what that means, it will be of the order of log n, but as it becomes more and more unbalanced, it will change from order of log n to order of n. So, this is because as the more unbalanced it becomes, the tree shape is almost becoming a list. So, you just have a list in this direction. So, binary search trees are fast if they are shallow. So, what I mean by this is, suppose you have 10 nodes, and with the 10 nodes you have a depth of say some x, the least x depth you have, shallow it is, the better it is, fast. Suppose the depth is very large for the same 10 nodes I am talking about, then the speed is very slow of the search operation. Basically, we are talking about the search operation. So, for example, if you have a complete tree, it is the most shallowest tree with that number of nodes. The disadvantage of a binary search tree is that its height can be as large as n minus 1, that is, if you have n nodes, the height can be even as large as n minus 1, that is, it is completely skewed, then it becomes as large as n minus 1 in case you have n nodes. So, that is the disadvantage of a binary search tree, ordinary binary search tree. So, this means the time, what does it mean? The time needed to perform insertion and deletion or any other operation for that matter is of the order of n in the worst case. So, if you have n nodes, it will take of the order of n, which is then you do not have to go for a binary search tree, right. So, that is the issue. Now, let us look at a balanced binary search tree more in detail. So, till now we were discussing about why you need, why the problem of binary search trees if you do not bother about balancing. So, if it has skewed, then what happens? Now, problems occur when, as I already told you, when one branch is much longer than the other. So, how to capture the notion of a sort of complete tree? So, if it is a complete tree, you will not have one branch be much longer than the other. So, we want to capture that concept of sort of complete. So, how do we do that? We want to keep the binary search tree balanced. So, as nodes are added or removed, so searching and insertion becomes remains fast. So, whether you add or delete nodes, you want the binary search tree to be as balanced as possible. Okay. The definition of balance changes, I will tell you as for different trees, we will tell you as we go along. Remember, in this module we are talking only about balanced binary search trees. Why I am telling this is later on we will see about non-binary search trees also. A class of binary search trees is called balanced if each of the 3 dictionary operations that we normally talk about, finding an element, inserting an element, deletion of an element of keys or element of a tree with n keys, can always in the worst case be carried out in of the order of log n steps. So, we do not want the time of these operations, important operations like finding, inserting, deleting. Remember, in inserting, deleting you have to find also. In all these operations, the keys that we store for databases or whatever, we do not want the worst case time to be greater than of the order of log n. So, that is what we are aiming at. Approximately it should be of the order of log n. So, what are the approaches to balancing trees? The first approach is do not balance. So, what will you have? May have some of the nodes very deep, worst case n nodes will have n minus 1 as the depth. So, that is one example. The other one is strict balance, that means the tree must be balanced perfectly all the time. It is good, but then it is a costly operation, because for every insertion and deletion you have to do this balancing. We will come to that as we go along. The other is pretty good balance. So, you are allowing a little bit of out balance, and that is what we are going to do. We are allowing a little bit of out balance, and or you keep it in any way you want, you adjust on accessing time you adjust. So, these are the 4 approaches to balancing trees, or they are also called as self adjusting. Now, we go to balanced binary search trees. Now, this kinds of balanced binary search trees are, now we said that approaches were do not balance, have perfectly good balance, or have okay balance, or do self adjusting. Now, what are the types of balanced binary search trees? You have height balanced. What this means is ensure that the height of the siblings are approximately the same. Now, this is where we are defining. So, we are saying the height of the siblings has to be approximately the same, approximately only, or you can have weight balance. Here we ensure that the number of descendants of a sibling nodes are approximately the same. So, you can keep height or the number of siblings. Descendants, it is almost the same, but it is treated in a slightly different way. We will be basically talking about height balanced binary search trees. Tree rotations, we spoke about in the learning objectives, I said something about rotation. So, these tree rotations are used to maintain the balance, whatever the condition of balance we are stating, to be balanced after every insertion and deletion. Now, let us look at balanced binary trees. Binary tree is balanced if the difference in height, now here is the where we are talking about what we mean by balance. So, if it is perfectly balanced, it is different. Here we say a binary tree is balanced if the difference in height between any node or nodes left and right subtree is less than or equal to 1. Now, you look at the first node here, first tree, you will have a node, its left subtree is having 2, its right subtree is having a height of 1. So, the difference in height is 1. Here you have left 1, right 2, again difference in height is 1. The other one you have left, again you have height is 2, left this same way. So, you have all these 4 are balanced binary search trees. They are not perfectly balanced, but they are balanced because the difference in heights between the left and right subtree is only less than or equal to 1. So, balance is the height of left subtree minus the height of the right subtree. Okay. So, for example, you have here height of 5, here height of 6, we are assuming that the triangle is a tree is balanced. The convention is the height of a null subtree is taken to be minus 1 and 0 everywhere means it is perfectly balanced, small everywhere balanced enough, then we say that we can do any operation of the order of log n. So, maximum depth is 1.44 log n. So, that is how it is, we are not going to prove that, that is the maximum depth you can have. Okay. Now, let us look at what we want a complete tree after every operation. Okay. So, the tree is full except possibly in the lower right. So, this is an expensive operation. So, for example, suppose we want to insert 2, okay. It is a binary search tree, remember. So, we insert 2 and we get a complete binary tree. So, the left has to be rebuilt as a complete binary tree. So, if you insert 2 here, normally what will happen, 2 will be inserted where? You will go to the left, it depends on what you want to do, but it will be normally inserted as a right child of 2, I mean of 1 as a right child, that is a normal binary search operation, it will be inserted as a right child of 1. then it is not balanced. But if you want perfect balance, you will reorder the search tree and you get like this, a complete binary search tree, but then that is a very very costly operation every time if you have to do this for perfect balance. Now, let us look at binary search trees again. We want to prevent the degeneration of the binary search tree, that is, we wanted to keep a balance without somewhat approximately good balance. So, a binary search tree can be set up to maintain balance during the updating operation. So, every time we do an updation, it can be an insertion, it can be a deletion, we want it to be balanced. When I say balance, we do not mean perfect balance. Our goal is to keep the height of the binary search tree such that of the order of log n. So, the purpose is to achieve the worst case running time of the order of log n for searching, inserting and deleting, that is our purpose. So, types of binary search tree which maintain this optimal performance are AVL trees, which we are discussing in this and the next module, red black trees, that is another type of height balance trees which we will be discussing also, then splay trees. We will be discussing these 3 type of trees as we go along. And then we have non binary search trees also, which also we will discuss. Now, first we will take AVL. Now, AVL trees maintain height balance. For each node, the difference of height between the 2 subtrees is in the range of -1 to +1. We are not expecting it to be 0, it can be -1 or +1. Red black tree is a binary version of a 2-3-4 tree. We will go to 2-3-4 tree only later. Here the nodes have a color attribute attached. We will go into detail about that later. So, the color can be black or red, and the tree maintains a balance measure which is called as a black height. So, here we are just difference in height, here we have a concept called black height. We will be going into detail about this later. Then we have the splay tree. This is a self adjusting binary search tree with the additional property that recently accessed nodes will be quicker to access. It is a very important property, because what have been accessed recently will be the ones that will be accessed again, especially in a database operation, database situation. So, here this tree does a self adjusting balancing, and it also ensures that the recently accessed elements of the tree are quick to access compared to other elements. So, we will see this. This is an interesting tree which is called the splay tree. So, basic operations such as insertion, lookup, removal will take of the order of log n amortized time. Remember, we have already discussed amortized. Insert and find rotates a node to the root. So, here it will try to take the node that has that has been accessed most recently to the root. So, that is what it does. That is the splay tree. We will be discussing splay tree in a separate module later on. Now, in this module, after we have discussed balanced in general, remember we are looking for an approximately good balance, not perfect balance. What does that mean? We are assuming that here AVL tree, the height of the left tree minus the left subtree minus the height of the right subtree, maximum difference can be only 1. That means, it will be -1 to +1, that is the range in which the height will be and the balance will be at each node. Balance is height of left subtree minus height of right subtree. So, that is the definition of AVL tree. So, with that we will go into this AVL tree. In this module of AVL tree, we will be discussing only rotations. So, here you have an AVL tree is a binary search tree with a balance condition. We have already seen that. Why is the name AVL? AVL is named after its inventors Adelson, Welsky and Landis. Now, no other meaning of AVL, the first letters of all the 3 of them. And it approximates the ideal tree. What is an ideal tree? As we already discussed, it is a completely balanced tree that we cannot have, it is too costly an operation. So, it approximates that. So, that is the AVL tree, and it maintains a height close to the minimum, that is -1 to +1, that is what we said. Now, let us look at a valid AVL tree. Before we go into that, remember AVL tree is a binary search tree first of all. After that, we are talking about the balance. So, for example, if you look here at 11, the balance is -1, right, because left subtree is 0, 1. At 17, again left is more than right, so -1. At we will come from here. At 82, at 85 it is -1, any leaf. 82 it is again -1. At 65 again it is -1. At 97 it is -1. At 88 it is +1. At 44 again it is plus 1. So, that is how you calculate height of left subtree minus height of right subtree. But if you note here, it is not a complete binary tree, which means that the leaves of the AVL tree can be on the same or at the adjacent level, not at the same level. That is the valid AVL tree. Now, it is a binary search tree first of all. It has an additional height constraint, that is all. For each node x in the tree, the height of x dot left differs from the height of x dot right at the most by 1. Height constraint satisfied, then the height of the tree is of the order of log n. This can be proved, but that we are not going to do that. Balance factor of a node is the height of left subtree minus height of right subtree, and an AVL tree has balance factor calculated at every node. Okay, that is what I tried to tell you then. For every nodes, heights of the left and right subtree differs at most 1, and so you store the current heights of each node. Now, let us look at this. This is a height of a AVL tree. So, if you look here, this is h minus 1, h minus 2. So, h minus 1, h minus 2 and h. So, maximum of h minus 2, h minus 1, h minus 2 plus 1 is equal to h. So, this is the way it is represented as a height. The height of an AVL tree is storing n keys is of the order of log n, and minimum tree is of height h. Okay. The height of a node is the height of, here we take some representation. The height of a leaf is 0, the height of a null pointer is minus 1, okay, just for calculation purposes. The height of the internal node is the maximum height of its children plus 1. Okay. So, this is general definition that we normally say, right. Here why do we say h minus 1, h minus 2? H minus 2 has more height. So, h minus 1 h minus 1 has more height, h minus 1 plus 1. So, that is the height of h in the root node. Now, let us take the AVL tree an example. So, this is an example of an AVL tree. Okay. So, the AVL tree is a binary search tree, as we already told. The height of the left and right subtrees of the root differ at most by 1. Okay. And the left and right subtrees are themselves AVL trees. They are balanced. So, an AVL tree is a binary search tree such that every internal node V of t, the heights of the children of V and can differ by at most 1, again and again we are telling that. Height of the empty node is minus 1, height of the leaf is 0. So, height of a node is equal to the maximum of the height of the left subtree height and the height whichever is maximum plus 1. So, let us just go there. So, you have 40, okay, you have 32 height 0, 17 is 1. Then okay, then we go from this side 48 0, 62 0, 50 is 1, 85 0. Okay. So, here between for the node having value 78, left subtree has 1 and right subtree has 0, we take the maximum of that 1, 1 plus 1 2, and for 44 you have 17 which has a height of 1 and 78 which has a height of 2. So, you have to take the maximum of that which is 2 and then add 1. So, that is how 44 gets a height of 3. Here we are talking only about heights, we are not talking about balance factor. Okay. Now, we will talk about balance factor. So, for each AVL tree node, the difference between the heights of the left and right subtrees can be minus 1, 0 or plus 1, and this is called the balance factor of a node. Height is common whatever may be the type of tree. Here we are talking about only the balance factor. So, here in this particular module we are defining the height to be height of left subtree, balance factor to be height of left subtree minus height of right subtree, and if balance factor is greater than 1 or lesser than minus 1, then the tree is too unbalanced, and what we have to do is we have to do rotation. So, to make the tree balanced. So, we talk about heaviness, this is just a term, positive balance factor, negative balance factor. So, if it is heavy on the left, then you have a positive, that means it is 1, okay. Then it has it is called positive balance factor. If it has right heavy, then it is called heavy on the right, then it is called it has a negative balance factor. Now, again we will talk here. Now, the yellow, what is marked in yellow are the balanced tree. It is the same example that we saw last time, but here we are talking about the balance factor. So, height of a node is h, balance factor is h left minus h right, and empty height is minus 1, as we already told. So, now let us look at this example. If you look at this example, balance factor 0. Now, 17 has balance factor h left minus h right, h left is minus 1, 0. So, you have minus 1. Then if you take here 48 as 0, 62 as 0, 50 is 0 minus 0, 0, and then 88 is 0, and 78 is plus 1, okay. Why plus 1? Because of the height difference of the left subtree. You should not take the balance factor difference. So, here you have 2 minus 1, so you have plus 1. Then here you have the height is actually 2 and here the height is 1. So, 2 minus 1, I mean 1 minus 2, so minus 1. So, that is the balance factor. Now, if the balance factor, what will happen due to insertions and deletions, then, it will change from 0 to plus 1 or minus 1, or if it has already a balance factor of plus 1 or minus 1, if it is plus 1 it will change to plus 2, if it is minus 1 it will change to minus 1, minus 2 or plus or minus that, and then we need to do a rebalancing. So, this is what is the basic essence of an AVL tree. So, first you have to understand the height, then you have to understand the balance factor. The balance factor is defined like this for the AVL tree. Now, let us again look at the properties. The depth of a typical node in an AVL tree is very close to the optimal depth of log n, where, okay. Consequently, all the searching operations will have logarithmic worst case bounds, which is why we started off with this process at all. So, an update or insert or remove both in an AVL tree could destroy the balance that we are talking about. So, we rebalance before the operation can be considered complete. So, when we do an insertion and deletion in a binary search tree, we do in an AVL tree, we do it like a binary search tree. So, you have to find the element where you have to insert, all that is the same. After that, we have to do a rebalancing if required, only then the update operation is considered to be complete. Okay. So, after an insertion only now this is an important aspect that we are talking about here, new aspect. After an insertion, only the nodes on the path from the insertion point to the root node will have their balance altered. Understand what I am saying? So, you have inserted at one point, from that point to the root, that path alone the node's balance factor will be affected. The other parts of the tree, the balance factor will not be affected. Okay. So, we talk about rotations. What are these rotations? This is a new term that we are coming across. So, insertion deletion involves adding or deleting a single node. Okay. So, it can increase or decrease the height of some subtree by 1, that is what it can do. If the AVL property is violated at a node x, that is at that node, the height of the left and right subtree will differ by exactly 2. Okay. Exactly 2 if there is, because from 1 it will go to 2, it could be minus 1 plus 1, all that we are not bothered about, but it will differ by 2. Rotation will be applied to x, okay. That is the balance is violated at x, you will apply rotation to x to restore this AVL tree property, that is the balance. Okay. So, let us look at this. Now, you have a tree, okay. So, I will just come to that. We have a tree shown there on the left and we are inserting 35, normal binary search tree operation. So, we insert 35. When we insert 35, what happens? The balance factor at the node 45 changes to plus 2. Okay. So, the deepest node, why deepest? Not the, after that also 50's balance is also affected, but that is not the deepest node. So, 3 adjacent nodes are required to restore the balance to a tree. The deepest node, that is 45, requires rotation to rebalance it. So, because ancestor of a deleted or inserted node whose balance factor has changed to plus 2, in this example it has changed to plus 2. So, there are two types of rotations, right rotate B or left rotate A. So, a rotation is a the operation rotation takes one of the order of 1 only. So, the idea is that rotations maintain the ordering property of BSTs. If it did not, then there is no point in doing a rotation. Now, if you look at this, okay, A, B. So, what you have done here is you have rotated it such that, right rotated it such that you have A going to B and B going to the A becoming the root and B becoming the right child of A. So, that is why it is called right rotate. The left rotate is the opposite, we will go into this in details as we go. Now, remember it is a binary search tree. So, obviously, a rotation should not affect that property, the binary search tree property. So, now let us look at this. You have a trees T1, T2, T3 subtrees and you have 2 nodes x and y. Now, I want to do a right rotation of x. This is how rotation is spoken about. You rotate a node about some point, another node. So, you are rotating x about y. So, what you are doing, you are taking, it is a rotation. So, you can see the arrow there. So, you take x and rotate it. So, now what happens, y comes there, and look at this, that T2 has been now added to y as y's left child. We will go into details a little later. This the same holds good for left rotation. Left rotation will be the other way around. I will come to that, but what we want to talk about here is that the BST ordering property, is it maintained. So, here we have in the initial this part we have T1 less than x, x less than T2, and x is less than y, and y T3 is greater than y. Now, let us look at the tree that has been obtained after the rotation has taken place. If you look at T1 is less than x, fine, x is less than T2, yes, and T2 is less than y, yes, and T3 is greater than y, yes, x is lesser than y, which is lesser than T3. So, if you look at both sides of the tree has been modified, but however, the binary search property has been retained. So, that is one of the main criterions of rotation, it should not be retained. Similarly, for left rotation. Now, again there are two types of rotation, a single rotation or double rotations. Okay. Now, violations may occur during insertion into a left subtree of left child, then we call it as single right rotation. The second case is right subtree of right child, then we call it as single left rotation. Case 3 is right subtree of left child, you see that it has changed, double, it is a left right rotation, and if it is left subtree of right child, again it is double right left rotation. This we will go into detail about why we need these type of rotations when we are talking about insertion. In this particular module we are talking only about the rotations. Now, let us go to single rotation. A single rotation, what it does is it switches the role of the parent and child while maintaining the search order. So, if x was the left child of y and you do a rotation, now x comes here, y has to come on the right, because the search order has to be retained. If it is the other way, you have a right child of x and you do a rotation. So, let us say x is the root and y is the right child, y is greater than x. So, when y becomes the root, x is less than. So, that order is retained. We rotate between a node and its child, that is how you do single rotation. Child becomes a parent and the parent becomes a right child when we do right rotation, and becomes a left child in the case of left rotation. The result is a binary search tree that satisfies the AVL property. So, it has to be a binary search tree, which we discussed previously. It also has to satisfy the binary AVL property. So, let us look at the first case. Now, what has happened in the first case is the left subtree of the child of the left subtree, that is the left subtree of x violates the property. Okay. So, when it is a left child of x that violates the property, we have to do a rotate right. So, what we are doing is we are taking y and rotating it about x. So, what happens, we are doing a rotate right, y is right child now becomes x is left child. So, this is a method in which the heights also you can see that the heights are before A and C had a lot of difference in height. Now, you are introducing a node there, so that height balance is also maintained, as we previously saw the binary search property is also retained. So, let us take an example. You want to rotate, we have seen this example, right rotate of x about y. So, actually what is happening is the left child of x, x of a node y, which was previously there, now becomes y's parent. Okay, that is the first step. Then y becomes the right child of x. Okay, this is for right rotation of x about y, and then if the right child of T2, if it exists, right child T2 of x, if it exists, now becomes the left child of y. These are the 3 steps in right rotation. I will repeat again. When you want to do right rotation of x about y, the left child of x, x of y, now becomes the parent of y becomes the right child of x, that is the second step, and the right child T2 of y, I mean the right child T2 of x, if it exists, now become the left child of y. So, these are the 3 steps, there is no other steps for doing this. Okay. So, what we have done is, now if you look at this side, you had T1 plus T2 plus T3, now it has become T1 plus T2 plus T3, now it has become T1 plus T2 T3, that is the method in which this has changed. Now, let us look at an example, or before we go look at an example, let us look at this step by step. So, let us assume that K2 is the node at which imbalance occurs. Okay. This is the node at which imbalance occurs. So, what we have to do? We have to first find out what is K1. K1 is equal to K2's left node. So, K2 dot left. Then now what we do? We do make K2 dot left be equal to K1 dot right. Okay, that is what we have done. So, B is K2 B is K1 dot right, that has been made into K2 dot left. Okay. And then K1 is now K1 dot right now becomes equal to K2. We have changed K1 dot right. Now, K1 dot right now becomes equal to K2 and K1 is returned. Previously the root was K2, now K1 is returned. So, these are the 5 steps. What are the 5 steps? First you have to identify the node K2, then you have to find K2's left child. Okay. I mean, which rotation to do we are not looking at here, what happens during rotation. So, we have to find the left child of K1, then what we have to do? You have to third step is make the K2 dot left equal to K1 dot right, okay, here in this case B, and then make K1 dot right, new K1 dot right equal to K2 and then return K2. So, this is single right rotation. Okay. Next we will see the case of the left rotation. The right subtree of the right child of x violates the property. So, the right subtree of the right child of x, so y's right child, the right subtree of right child of x is y, its right subtree which is a violates the property. Then you have to do a rotate left, that means you have to rotate y about x again, but in a left direction. So, left rotation of y about x. So, here what we do, the steps are this: the right child of y of node x becomes x's parent, okay, and then x becomes the left child of y, and then the left child T2 of y, if it exists, now becomes the right child of x. So, these are the 3 steps. Again we will go again one more step further. Again now what happened? T1 plus T2 plus T3 now becomes T1 plus T2 plus T3, as you can see from the brackets. Now, again the steps. Here what has happened? We have identified the first step before rotation, K1 as the node at which imbalance occurs. Then we find K2, K2 is nothing but K1's right child. So, we find K2, that is the second step. Then what we do? We make K1's right child to be equal to K2's left child. So, that is the third step. The fourth step is we make K2's left child to be equal to K1 and then we return K2. So, the same 5 steps in another order. This is the rotate left property. So, that is about single. So, what did we do? We rotated once, that is y about x, this way also y about x. So, this was called right rotation, this was called left rotation. Now, we are talking about double rotation. When a new item is added to the subtree of an inside grandchild, I will tell you what that is. The imbalance is fixed with a double right or left rotation. A double rotation is nothing but 2 single rotations. So, there are 2 cases here: left inside grandchild, left right double right rotation, right inside grandchild, right left double left rotation. Okay. So, a left right double rotation is equivalent to a sequence of 2 single rotations. So, the first rotation of the original tree, a left rotation between x's left child and the grandchild, and second rotation of the new tree, a right rotation between x and its new left child. You will understand this better when we take an example. We are talking about left right rotation. The right subtree of a left child of x violates the property. So, if you look at this, x's left child, okay, is y, y's right child violates the property. So, when that happens, then you have a left right rotation. Please note that right subtree left means you are doing a left right. So, the first rotation would be rotate the tree left about x's child and grandchild. So, you are rotating z with respect to y. This rotation is a left rotation which we have already done previously. So, that is what is being done. Now, you have the new tree with z and y, z and x. Now, you rotate z about x. What rotation? Right rotation. Rotate that is the tree we got, you rotate it and you get this. So, example, you the deepest unbalanced node you take, that is x in this case, then first pivot is the left child of the deepest unbalanced node, here v, and you left rotate w about v. Okay. So, that gives you this. So, now T1, T2 plus T3 plus T4 becomes T1 plus T2 plus T3 the whole thing plus T4. So, that is the left rotation. Then now you have to, the second pivot is the deepest unbalanced node. So, now you have to rotate w with respect to x. So, right rotation of w with respect to x. So, that is what happens and you have the balanced. This is the left right double rotation, and now you have the tree as T1 plus T2 plus T3 plus T4. Now, the right left notation, here left notation is equivalent to the sequence of two single notations. First rotation is a right rotation of x's right child and the grandchild, and second rotation is a left rotation between x and its new right child. So, again similar to what we did before. So, we can just go a little fast. This is the left subtree of right child of x violates the property. So, what we do is we take first we do a right rotation of z about x, okay, and we get this, and now we do a left rotation of z about x. So, z about x, and so we get this particular tree. So, here are the steps. The first pivot is the right child of the deepest unbalanced node, which is w, and then we do a right rotation of v about w, and we get this tree. Now, the second pivot is the deepest unbalanced node, that is x, and we do a left rotate of v about x, about x, and we get this node. So, this is the node before the first rotation, this is after the first rotation, this is after the second rotation. So, what have we done? We have explained the concept of balancing and balanced binary search trees. Then we looked at the properties of AVL trees in general, and we looked at two different rotations of AVL trees. We have not seen how the deepest, that and all we have not seen. We have just described the single rotation of AVL trees and discussed double rotation of AVL trees. If you would note, we have not looked at examples per se with numbers and actual trees, because that we will do in the next module when we are discussing insertion and deletion. So, thank you.